Introduction Diving Project. In Phase 3, our knowledge on the 3D Euler dynamical equations was tested. The dive that we had to analyze was open to pike to dance and back to open. The pike and dance configuration led to a moment of inertia matrix. Thus, we had to use the 3D Euler's dynamic equations to account for the change in the moment of inertia matrix. Additionally, to verify our data, a simulation was made where the dive went from open to pike from 5 to 10% dive time, pike to dance from 70% to 75% time, and dance to open from 90% to 95% of the time. Moreover, the number of flips and twists was calculated. As a way to conclude our project, a new simulation was developed where the goal was to create a perfect high-scoring dive. Introduction Human Body. The body is composed of 8 members: a spherical head, a cubed for the torso, and then 2 cylinders for the upper arm, 2 cylinders for the forearms, and then 2 legs. The dimensions of the body are proportions of the height, age, and in the case of the mass, each member is a proportion of the total mass. As such, the main values to consider are age, which is height, is equal to 1.8 meters, mass is equal to 60 kilograms, that's the mass of the total body, and then the gravity, which is equal to 9.81 meters per second squared. These rigid body members may be treated as separate entities for the purposes of moment of inertia calculations. They were calculated with respect to the center of mass using the parallel axis theorem. As such, our calculations were made taking 3 configurations in consideration: open, pike, and dance. To the right, we can see the boulder proportions, which is the first image, and then the body configurations, which is open, the first one, pike, the second one, and the third one is dance. Now, for the calculation of the center of mass, first we took into consideration the point about which the coordinates of the center of mass needed to be determined. In our case, it's the center of the torso. After our reference point for the center of mass was determined, it was time to calculate the center of mass for the x, y, and z coordinates using the body's coordinate locations relative to the selected point. Rigid bodies can be split into multiple shapes such that the calculations of their individual center of mass is simple. In the case that the body would not have been of uniform material, the density then would have been considered and the same process would have been done. After the center of mass and the shapes conforming the body are calculated, we then use the center of mass formula, as is shown below, to calculate the center of mass of the entire body, which means that it will be the sum of each of the body parts, specifically times its x location divided by its x location with respect to its center and the total mass. The same it will be for the y and the z coordinate. Calculation of moment of inertia, MOI, and product of inertia, POI. For the calculations of the moment of inertia with respect to the centers of mass of each body part, we use the formulas for each of the members of the body: sphere, cuboid, and cylinders. Now, to calculate the moment of inertia with respect to the entire body for the respective axis, the parallel axis theorem was used. In the case of the product of inertia, if the body was symmetric with respect to a particular axis, then it will be 0. For instance, if I want to calculate the product of inertia Ix, y, and then the body is symmetric with respect to the z-axis, the product of inertia would be 0. Such as the case of the open configuration. Nevertheless, for the pike and dance configurations, this does not apply. For the parallel axis theorem, in case of the product of inertia, the image is the one to my left. And then for the parallel axis theorem, for the moment of inertia, the formulas are to my right. Calculation of moment of inertia, MOI, and product of inertia, POI, part 2. For the calculation of the dance, the direction cosine matrix was used, considering the rotation angles of all the body members, arms, and legs, that each was at 30 degrees with respect to their own coordinate system. The purpose was to calculate the moment of product of inertia matrix using the same coordinate system as the rest of the body. Once we had this, we had the moment of inertia matrices for each body part. And then the parallel axis theorem was used to convert the moment of inertia matrices around the individual body centers of mass to those around the overall system center of mass. Once this has been done, we summed all the moment of inertia matrices to get our result. This is one of the direction cosine matrices. Calculation of center of mass and moment of inertia. These are our results for open, pike, and dance in terms of the center of mass coordinate, and our moment of inertia matrices for open and pike as well as dance are to my right side. Calculation of the initial condition of the center of mass velocity and corresponding center of mass response. For the calculation of the initial condition of the initial velocity of the center of mass, the projectile motion equations can be used. As we can see in the graph from the bottom on the right, it's the motion, the total motion of the dive. In terms of the velocity, it can be split into two components, one in the x component and the other one in the y component. The equations that we used are on the upper right side of the slide. So the first equation we use to calculate the initial velocity on the y component. As you know, in the projectile motion on the highest point, the vertical velocity, the y component of the velocity is 0. As such, the first equation was used to calculate the initial velocity in the y component. The second equation we used to calculate time and the final velocity. And then the third equation, we use it to calculate the velocity on the x component. The fourth equation was used to calculate the total time, which was, the time was divided between two parts. The first part was when the body was in the moment from the board all the way to the highest altitude, and then from the highest point all the way to the water, and then the velocity, the magnitude of the velocity is using Pythagorean theorem, the x component of the velocity and the y component of the velocity, which gave us 7.73 meters per second. And then this is a plot of our velocity of our center of mass in the x, y, and z components. And then our code is as shown to the right. Mind you, the velocity in the x component is constant, as we know from projectile motion, and the z component, we never had a z component in the center of mass. And then the y component is as shown.
Hi, so I'm going to be talking about the solver I built to simulate the full range of 3D dynamic motion. In order to start, I want to go over this differential equation on this slide right here. So we have this equation where the moment is equal to the product of the moment of inertia matrix and the angular acceleration plus the product of the rate of change of the moment of inertia matrix and the angular velocity, and this cross product of angular velocity and angular momentum. Because there's no applied moment, we can actually set that to 0 and then start rearranging the equation. What you get is an expression that looks like this in terms of all those variables I listed before. And as you'll see as I go through it in just a sec, all these variables are going to be things we can basically know or figure out. So now that we have this equation, we can see how the simulation actually works. So the main way it works is by using the same function to calculate the relevant values for all steps of the dive. So this can work for any dive at which there is a constant, including a 0, rate of change in the moment of inertia matrix, which is an assumption we're allowed to make, that it changes either constantly or does not change at all. And you'll see at the bottom here, if I just highlight this with my laser pointer, right? We've got the inputs to this function for all values across the entire dive from 0 times t total to t total, which is the total time of that dive. And here's how the loop actually works, right? We've got our inputs, and we have our little time step variable, delta t, which is 1 times 10 to the power of -5 for increased fidelity. And it's basically a linearizing differential equation solver that I built. So first of all, we find our rate of change of moment of inertia, which is constant. And we find this using this little function here. I don't have it on screen, but it's very simple. What it does is it subtracts the final moment of inertia matrix, or it takes the final moment of inertia matrix and subtracts the initial moment of inertia matrix, and then divides that by the total time between them. Then, across the time interval that is provided as an input to the function, so that's, while t is less than t2, we use that equation we talked about to find our angular acceleration. So you can see that's this function right here. We know our moment of inertia because it's either our starting parameter or we've incremented it, as you'll see soon. We know our rate of change because it's constant. We solve it before we start the while loop. And then we know our angular velocity because it's either initial value or we'll increment it, as you see, right? We find our angular acceleration. Now that we have this angular acceleration, we can use it to increment our angular velocity. So we just say it's omega equals omega plus delta t times omega dot, right? The increment in the moment of inertia matrix works exactly the same way, where we're multiplying this rate of change by the very small time step. And then we have h equals I times w, right? We save this h value, our angular momentum, to this vector right here. And this is what's going to allow us to plot our angular momentum over time. And then we increment time. Now, as you'll look right here, I've generated, using this momentum vector, a plot of my momentum over time. Now, it looks like it's varying a lot, but if you actually look very closely at the y-axis, you'll notice it varies between 49.745 and 49.77. And what that means, right, is that you have a very, very small variation in momentum. And the x-axis is just time as a fraction of your total dive time. So what this shows us is that even without directly programming it into our simulation, angular momentum is conserved. Okay, and yeah, now moving on.
In continuation of phase 2, our next goal is to find the velocity and acceleration of the center of head and the center of mass. Here are some of the parameters that were used. To begin finding the velocity of the center of mass, we can use basic kinematic equations where the final velocity is equal to the initial velocity minus gravity times the change in time. And this will cause a decreasing velocity in the y direction, but the x and z direction of velocity constant, and this can be shown in the graph. And for the acceleration of the center of mass, there will be a constant g throughout the dive, and this can be shown in the graphs as well. We list more parameters to solve with the center of head, and this loop will help calculate the center of head by using the 2-point formula, where we're solving for angular acceleration and updating the angular velocity as well. And this will also help calculate the load factor. And after this is done, these were the graphs that were produced. In phase 2, our first task is to find a number of flips from the initial angular velocity from phase 1, and our second task is to find the initial angular velocity to achieve 2.5 flips. So the main purpose of this code is to create a function is to simulate the divergence motion based on an initial angular velocity. It uses the divergence moment of inertia in the two configurations of open and pike, and you know that the moment of inertia changes during the dive as the dive transitions between these configurations. In this function, we are also calculating the angular velocity, position, and acceleration over time, which are needed for plots. And if we run the function with our initial angular velocity from phase 1, we get an approximate flip of 1.4103. And if we assume that the number of flips is directly proportional to the initial angular velocity, can get an initial angular velocity target of about 2.9038, and if we run this initial target angular velocity inside our function, we get exactly 2.5 flips. Here are the plots. With phase 3 of our diving project, our goal is to simulate a complex dive where the diver transitions multiple configurations from open to pike to dance and back to open, while tracking the resulting number of flips and twists. As always, we always list our parameters, or we're using our total dive time, the initial angular velocity calculated from phase 2, the moments of inertia of each configuration, and the different time segments we're going to use. In this code, we will be using the OD45 function in MATLAB, as well as several helper functions. The diving dynamics helper function will implement Euler's equations of rotational motion and calculate angular acceleration and rate of change of the diver's orientation angles. The gate configuration helper function will determine the diver's moment of change and its rate of change based on the current configuration based on the time segment. And after, we will be using the get transformation matrix to convert our calculated angular velocities from the global frame to the torso frame. And if we run this, we get in our global frame, we get flips of 3, a twist about 0.1, and a side slip of 0.167. And after the transformation into the torso frame, we get a flip of 2.3, a twist of 0.8, and a side slip of 0.026. For phase 3 of our perfect dive, the goal of this code is to simulate a dive with added complexity by optimizing a sequence of configurations, starting with open, transitioning to pike, then dance, and adding a new configuration of pike, and finally ending up in open, all while tracking the flips and the twists. Of course, we first look at the parameters, and we ended up choosing an angular velocity that was increased by 8% to get at least 2.5 flips, a side slip of the 0.15, which is less than 10% of our angular velocity, and a twist component of exactly 25% of our angular velocity. And this code is exactly the same as the last code, using the ODE45, the 3 helper functions, but we added an additional configuration and time segment between the transition from pike and from pike to open. And if we run this code, in the global frame we get rotations of 3.4, a twist of 0.1, and a side slip of 0.1. And in the torso we get a flip of 2.7, a twist of 0.3, and side slip of 0.009.
Let's look at the visualization methods for the diving project. So right here we have 4 main principles, or 3 or 4, let's see. So use rotation matrices. This is the key principle that you need to keep in mind whenever you're coding. You need to make these rotation matrices such that you can make a picture, and for every frame, rotate a certain theta. As you see here, we have our flip rotation, our twist rotation. Now, this is just the wording I use so I could differentiate between the omega z and omega y, omega z being the flip rotation, the omega y being the twist rotation. You can see that the z one's going to have the 4 angles within the top left quadrant, those 4, and the twist rotation is going to be just like the y-axis with them at the 4 corners. Okay, so modify the mass and moment of inertia by configuration. Okay, so yeah, we had three configurations. And so this is just a snippet. So this is a case when I went to straight and the transition to pike. Recall that we needed to have the timing, right? So the time between each one. And in MATLAB, the way I did this is by case. So if my t, which is my frames times my time taken throughout, I would multiply it by a fraction, and then I would update where my torso was, and I would have it in frames. So I would essentially just kind of snapshot it into this orientation. And if it's in this orientation, I knew its center of mass had to be this. And the fraction represents the portion of time of frames that it would have right there. And then update and plot with plot three. If you look down here, plot three, we can use the notation of MATLAB, the K dot for lines, R dot R dash for the stick figure, and then B dash for its torso for its legs. This was just to make a stick figure body. We just needed to have the orientations such that you could tell when they were at different points in the dive. So I did this by size. So the stick figure is made larger whenever it's in different orientations. I made it 1.2 in this phase 3, 1.2 for when it's in pike, 1.5 for when it's in dance, and its original size for when it's in open. All right, so let's look at these over time. All right, so phase 1 visualization. Let's look at this. Uh, this is rudimentary. I did like the IM rotate. At this point, I did not use I could get away with not using rotation matrices. I went on to using rotation matrices later to calculate that of the stick figure in the second phase, but in this one, I just rotated the image. And it's kind of, I still got the projectile, but it was kind of a crude image rotation because of the background. So we improved upon this in the second phase whenever we have. So as you can see, midway through, this is where I start using the fraction of my frames to tell you when I'm going to have my diver at its orientation. You can see I also did a 2D stick figure here, and it's a little bit easier to animate a pike than it is a dance in 2D because all you have to do is make two perpendicular lines. But in the third one, we need to get around this and make it still a visualization that a non-engineer could look at this and still be able to tell when they're changing orientation without very, very advanced animation graphics and animation skills. The third phase. All right, so here's a base dive. This is one with 2.5 flips and one full twist. Okay, you can see the size of it peaks at the top, and it just changes automatically the size. It looks a little bit smoother than it is. In real life, it's from 65% to 40% is when it's in base. That's when it peaked in size, and that's its 1.5 size I was talking about uh for the dance. And then the time when it was like transitioning, that was its pike. And when it was its original size, as it is right now in the stopped picture, that's when it's in open position. Okay, so let's look at the pretty dive. Here we did 3.5 flips and a 0.5 twist. This is done by adding a pike after the dance, such that it goes open, pike, dance, pike, open. The reason that this will twist less is because it spends less time in the dance. Therefore, it has less time in a orientation that has products of inertia, such that it would have to have a twist to it, right? So let's look at the conclusion here. All right, so conclusion. So what do we do during this lab and during this project? Um, we calculated the center of mass at different mass location at different configurations, meaning that based on how this character was oriented, we needed to look at its center of mass such that we could look at its rotation, and this affected its moment of inertia. And by its moment of inertia, we created matrices that described its moments of inertia and its products of inertia, such that we knew how omega y and omega z were affected at different orientations at different times throughout the projectile. All right, so we use ODE 45 in MATLAB to simulate dives and generate plots for analysis and for viewer understanding. This is so we could see how many flips it would take at different mode of inertia matrices, right? This was a skill we developed over this lab because we could look at the plots and it will allow us to see how it's changing. We could look at the change in I because when it's transitioning into like pike or into dance, we can see how the change is a linear over time. That's how we treated it. All right, and then we visualize each dive in MATLAB such that a non-engineer can understand the body mechanics of the dive. A big component of this project was making sure that this project is viewable by a non-engineer audience, someone who hasn't done this project for themselves. And I believe this visualization will allow the viewer to see what the diver is doing uh, at a base level, and it should allow for good understanding. It's been a great lab, and thank you for your time.